pleased to have Andrei Okounkov from Colombia, who actually was one of our first speaker on the Mach9 theme front when this started several years ago. And once again, it's a great pleasure to introduce a fantastic mathematician, a great humanitarian, a friend of mine of many, many years, Andrei Okounkov.
Thank you, Neil. That's great to be here. I hope it's I didn't misrepresent the subject by giving my intention was to give really accessible talks. I hope you can all be with me in this. And so this is maybe today my plan is maybe to explain some sort of phenomena in the world of special functions in which some geometric considerations, which will probably start with the geometric consideration, will probably happen tomorrow, where they really shed light on classical questions. So, okay, so special functions, of course. You make special function with the, imagine this is like you go, a line like a list library of special functions, and you have hundreds and hundreds of pages of formulas. And okay, let's start with the simplest one. Let's start with just the spherical harmonic. I'll try to draw an n-dimensional sphere. I'll explain what I mean by the drawing. It will be this is the first coordinate x1, the second coordinate. But this is an n-dimensional sphere, so there is if I want to rotate around x1, there's the whole. So this is Sn minus one dimensional sphere. The whole thing is an n-dimensional sphere. And I'm interested in spherical functions. Our eigenfunctions, the Laplace operator, there are invariant. In this case, the ones I want to look at are the ones that are invariant under rotation, and this n minus 1. So they're really just function of x1. But it's maybe better for us, instead of thinking of the function of x1, thinking a function of complex variable z, which if I slice this with the x1, x2 plane, I can write the z as x1 plus I x2. And so I'm interested in these functions of z, which this S minus one dimensional sphere, this will intersect, of course, intersect the same S1 also in the complex conjugate point, which since it's absolute value 1, I can also write Z. So I'm interested in functions of Z, which is invariant under Z goes to Z inverse, and altogether this has to be eigenfunction of the Laplace operator. So what's Laplace operator? So what's the volume of this Sn minus one dimensional sphere? The volume of Sn minus one dimensional sphere, well, it's like the volume. Just try to write it down. Is proportional to Z minus Z. The sine of the angle here. This is no natural talk right now. And so if we minus the Laplace operator, again, maybe after proportional, after constant. Important. This is what's up to. This has to be a second order differential operator with the leading coefficient of replacing Laplace operator by minus Laplace operator, we often do, it will have to start with z d by dz square. So the correct has to be two derivatives in the z d by dz direction. It cannot have any constant term because it has to kill Laplace operator has to kill a constant function. And so the z d by dz term, well, let's say if we call this function b of z, this since it's cells of a join, it has to have the form. Has to have the form z by dz of dz divided by dz. That's just from self-trigger. So concretely, this will come out to so this would be volume raised to the power 10. I invite the audience participation in silly titles like this. And so the result would be there would be this n minus 1 here. And here I'll write the partial right is like z squared plus 1 over z squared minus 1. So this is the polar proportionality constant because they will multiply d by any constant that cancels out of this fraction. And so now if we think of this equation not as an equation, and so this is applied to some function minus some sort of eigenvalue, applied to some function. Since we have z, it's only z squared that enters this formula. So if we have a, might as well apply to the function of z squared. And so this is in the variable z squared. This is maybe the first trigonometry lecture. So this is if I introduce this, if I think z squared is a variable, this has square. If this variable has 3 singular points, namely z equals 0, infinity, and 1. And so it has to be, since this is a hypergeometric equation, second order with 3 singular points.
These are the singular points of the differential equation.
Yeah. 3 diagonal singular point hypergeometric equation. And has additional feature, it's evidently symmetric. Symmetric in z goes to the inverse. The special feature. So the general hypergeometric equation depends on 3 parameters. If I impose the symmetry, it will depend on 2 parameters. And the 2 parameters here are this n minus 1 and this eigenvalue here. And so that this is solutions of this equation. Just write you an answer. Solutions are one thing is you write z to the power of, let me introduce some variable t will be variable n minus 1 2, and yeah, I'll introduce variable a. Let's say lambda is maybe like 8 squared, something like that. It's not important. Look in my notes, but maybe it's not important. And so that the solutions are have the form here. A plus this t over 2, and then this hypergeometric function, so like t1 of t a, and so this one variable of the hypergeometric function is always kind of like equal to 1. I'll write it. and here will be 1 plus A, and then Z squared, and others. So this with this parameterization equation is symmetric with respect to A goes to A inverse, so minus A, there is another thing. And so when is this actually an eigenfunction of Laplace operator? It's easy to convince yourself that this can be actual. So this is some. So right, I didn't say what's a hypergeometric series. So you introduce F classically 1 classical A B C Z. This is summation over D Z to the D, and then something called Pochhammer symbols. Wait 1 second. D sub D, D sub D divided by C sub D, where this A sub D is a Hammer symbol of factorial power. And this is A times A plus 1 times A plus 2 and so forth. A plus D minus 1 altogether 3 terms. And it's must be easy to convince yourself that this is, how can this be ever symmetric in Z goes to Z inverse with some series in Z that goes ad infinitum? Can only be the only solution that is interest of us. So sorry, I forgot it. Not A here. T plus A. The only way this can ever be function of the kind we want if this series terminates. What does it mean? The series terminates. This means at some point, if this number is a negative integer, that at some point you hit a 0, and then you just all terms starting from some point on will be all 0. So the only eigenvalues this has to terminate. And how can this terminate? It's this number here that has to be equal to minus k. K, this is the number of the eigenfunction. And then this would be really nice, because this will terminate at the last term. You will see this will be something to the power z, which is 2 times this. It will be like 2 times this number. Sorry, then I don't need this one half. I was thinking one double. So this is A plus T. This will be exactly equal to this minus K. And so this has a chance to be symmetric with respect to that inverse. In fact, that's this analysis of spherical functions. And if you don't want the termination condition, if you just want this, if you want a non-terminating thing, then all you need to know is to replace a sphere by the corresponding hyperbolic space. Sphere is a symmetric space corresponding to root system A1. This is the compact form of that symmetric space. The corresponding non-compact form of the hyperbolic space. In the hyperbolic space, the whole thing is the same, except you really need the combination of the two, which there is a combination. There's the solution, which is symmetric with respect to that. And that's your eigenfunction, but the space being non-compact with spectrum theory is not discrete. But we will talk more about the function. And the next thing we want to consider is the Q analog of this expression. And what's a QM? So this is this this is the kind of the QMs are the kind of thing that well, I'm not a historian of the subject. Maybe Richard will somehow say something more accurate. But I thought the first people discovered there's some magic to this in the formulas, and later they had all sorts of arguments why this magic happened. And so this is it certainly goes back to mid 19th century. The work of people like Heine, they 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 realized that there's something there's something. So this would be a theme in this lecture. There's something strange about this function. So this function is here we see like like we have here's like an actual power, and in A we have a factorial power. In Z, in the function Z, this solves a differential equation. Solves a differential equation in Z, while in the functions a, b, in the variables a, b, and c, in these variables it solves a second order difference equation. What does it mean the difference equation? So the difference equation means you have some function solve the difference equation. If it's so instead of an operator derivative, you consider the difference derivative. Postpone discussion of QNL for a second. The difference derivative. Namely, the value of function some value plus minus. We're doing numerical analysis, so this is somehow in some sense much more fundamental than the actual. And the difference equations in these parameters A, B, and C, there's classically what's known continuity relation for functions. They say how if I shift the variables A, B, and C by one or by two, then how this is expressed in terms of your original hypergeometric functions. This is it. But there is a different there's this story can be seen as a slightly unbalanced limit of a story which much more balanced, where instead of a difference derivative, you consider Q difference equation. So the Q difference equation they constrain instead of values you use addition of numbers to move the argument. Instead you use you shift your function for higher order equation, you shift your function by using multiplication to shift that. So this is the we're Q some parameter, not some actual function. So when we think of the difference equations, that's usually in the context of maybe some, especially in technology, you maybe think of you're going to shift by some variable epsilon. But then, of course, just rescaling the variable z, you can make this epsilon b1. But in the multiplicative situation, there is no automorphism of the multiplicative group that gives you possibility to get rid of the parameter q. Q is an actual one. So instead of dealing with these factorial powers, you really deal with maybe first thing first. That if I the first the main fundamental ingredient is the Q gamma function. Okay, there's many definitions of Q gamma functions, but maybe one I matter of case how to normalize Q gamma function, but maybe the one I want to normalize is if I take define Q gamma of x of z, I write it as 1 over 1 minus z, 1 minus qz, 1 minus square z, and so on. That's my term. And why is this? Can be called a Q gamma function? Well, first of all, this solves the Q difference equation. Just if I take this and shift it by Q, well, what's going to happen? I will lose the first term in this product. So it's going to be 1 minus z, which is the analog of gamma of x plus 1 equals x times gamma of x. And well, you think, why is 1 minus z analog of x? Well, x, what is x? X is the simplest possible function that vanishes at 0. And 0 is the identity with respect to the additive group law that we use to define this function. And similarly, if we use multiplicative group law, it makes sense to consider the simplest possible function that vanishes with z is the identity multiplicative identity, which is 1 minus z. And so, right, I forgot to say that this here, in contrast, there's a kind of a divergence, or you need to regularize. There is some sort of infinite product for the gamma function, but the gamma function for the Q gamma function, this actually converges. Converges if this written like so, if the absolute value is less than 1, this actually converges and has poles at z equals 1, Q inverse, Q minus 2, and so forth. This is this again multiplicative analogs of poles of this guy for this function has poles. And 0, 1, minus 1. The multiplicative analog of this are this. And this is this expression here, where this is the ratio. If you look at the special function books, this is how it's going to be defined. This is a ratio of gamma functions. Instead of writing a ratio of 2 gamma functions, I can write a ratio of 2 Q gamma functions. And now comes the kind of so if I take a ratio Q gamma, ratio of Q gamma by Q gamma, then I can write this as A Q D, which is A, sorry, one minus A, 1 minus QA, 1 minus Q D minus 1. Usually people don't write this Q and let the reader figure out whether they mean this or they mean that. And so with this after this discussion, maybe it would be logical to introduce the Q analog of the hypergeometric function. I use what's for that, right? And the one I already want, I'll just introduce the one I really want. So it will be TA. So the analog of instead of a plus, you have to write time. And instead of 1, I have to write Q instead of the QA. Instead, let's not do that. So this is the summation of T, the and now comes T. Well, I'll write it once with Q. T, 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 divided what? You write Q, Q, T, which is, so this is the expression, this is the Q analog of the factorial, so this is 1 minus Q, 1 minus Q squared, so forth, 1 minus the T. And then Q, A. And you really now see that this is really, the formula really looks overloaded if you really carry all these Q's here. So maybe with your permission, maybe I'll just erase them all. So as long as there is at least one Q anywhere in the formula, it's clear that you're talking about the Q of 100 signals. And there is one Q in this one. And so now looking at this formula, what we were doing here? What we were doing here, we were looking for terminating cases of this here. So this is a terminating case. Well, it's similarly exactly like this. So terminates if now we'll write T. So the multiplicative analog of this relation is T times A equals Q to the minus K. And so then you get some polynomial. P, K. So this is an equation on A. We think of it as an equation on A, so this will be an equation on PK of that is covered depending on T. And these are the I don't know if somehow having leaving enough space for the significance of what I'm going to write. So this expression here is the McDonald. Well, yeah, McDonald polynomials have some kind of root system, depending that for the root system. A1, which was the root system for this sphere. The sphere is symmetric. Hyperbolic for this root system. So in general, there's some for every root system and something and the parameter. So parameter t for us. Remember the t has to do with the dimension of the sphere, and the dimension in this part of math, this translates into some kind of multiplicity function on the set of roots. And here for this root system, there's one root and has some multiplicity function which is dimension. And for every root system, there's some polynomials called Jacob polynomials or Jacobi polynomials that include the spherical functions for the corresponding symmetric spaces, but also makes sense. So this expression here was making sense whether or not this variable t was n minus 1 over 2 but this expression doesn't really matter whether this number is half integer or not. So this is defined for any sort of multiplicity function on the root, and they have analog called McDonald polynomials, which are the Q analogs of them. And why did McDonald introduce his functions? So mostly maybe we should ask McDonald, but one fundamental reason he introduced it somehow. So this is there is one limit from this Magellan polynomial. One limit if I set q q and t both go to 1, and it arrays such that the log of t base q, this goes to something fixed. So this I write it additive. We had a parameter t, so this would be a new parameter, but this is really the additive t. Already old t. Then this goes to the old this goes to the old story. This goes to this spherical function. Or I'll write as n where n minus 1 is equal to t. But there is, instead of q goes to 1 and t goes to 1 limit, there is another funny limit. Well, I don't know, funny or not, it's an important limit. You can instead since q goes to 0. And as you do this, you get spherical functions. Spherical functions for what? You get spherical function in this case for a p-adic symmetric space, which is the p-adic symmetric space corresponding to the stable system I want, and in this case it will be SL2 over field of p-adic numbers. If I divide it by SL2 over field or p, so p is now the analog of the multiplicity, and the condition is that p is 1. This is the multiplicative. The t doesn't t fig. T is somehow fixed. You don't have to send t anywhere. T is just prime number. And what does this spherical function look like here? What does this space look like? The space is actually this particular space, that's just an infinite p-valent tree. So let's take some p, which is something like, let's take p equals 3. So there's a each vertex has p plus 1 neighbors, and we draw the trees. The center, something like. I'm getting tired of doing this. Okay, you get the idea. And so this space has also Laplace operator, I mean just a graph Laplace is. So if you want to, so what's the Laplace operator on the graph? If you want to know the value of the function of Laplace operator, you take the average over all neighbors. Let's see. And so that and the spectrum, since the tree is obviously unbounded, the spectrum of the Laplace operator is going to be obviously continuous. But what becomes discrete is where we're going to compute that function. So so again, spherical, right? Spherical function means it's invariant under, it depends only on previously we were looking for eigenfunctions, which were depending only on you can phrase it, only on the distance from the North Pole. So if you think of this as the analog of North Pole, then you're asking for functions that depend, take the same value on all this kind of spheres. So there's a sphere. You want the function to take all the same value T. And then, so this is the value. You can normalize the value of the 1 to be 1. And then this your PK Z Q T. This is sorry Q 0. This has to do with the value. This is more of the value of spherical functions. At points of distance. Okay? Where Z, so this object is invariant with respect to Z, that goes to 1 over Z, where Z records the eigenvalue. So Z plus Z1, that is the eigenvalue. So in this limit, there's a very interesting change of perspective. What was when we did spherical functions, the discrete index, we had a compact space. Discrete index has to do with the number of the eigenfunctions, whereas Z, it was an actual space, an actual continuous variable, and that was Z. Here, the space is discrete but infinite, and so there's a position of where you want to compute your function becomes the index, the discrete index, whereas the eigenvalue of your Laplacian, which is not continuous, well, it goes here. So you think, what's going on? Well, I don't know if you think that, but you may think, but what is this? But in fact, so the most interesting thing is that there's an exchange between the role of the argument and the label. But very remarkable fact now, which is fundamentally maybe why we have to go to the Q analysis. There's a very well, I don't know, maybe I'll write it very surprising. I mean, I don't know if it's surprising for you, but it's surprising. Label argument symmetry. For Magellan polynomials, namely if I take the k, put it in the middle, and I evaluate it at the point of the form, I take q to the m t, and I normalize it by its value as just q to the m. Oh, sorry, q to the t. This object is in fact is symmetric. So this is exactly just really symmetric, and this is absolutely symmetric. This is kind of maybe already on this level. It's very surprising. It holds for any root system. There's a general results to that effect proven by unique, except if you have a general root system, you have to take the dual root system on the dual side system. You don't with some root system. Just want to change the label. Label and argument, they live on dual Tor in general, so they or dual lattices in general, so they have to the dual lattice. But but maybe I'll explain a little bit of what would that symmetry is like maybe for JL1. It's just no root. So there's a group JL1 has no root, and for it the analog of McDonald polynomials. So the symmetry then has to do with the fact that if I look for things, so ordinary object of ordinary representation theory are characters for reducible representations for it. And for GL1, what I look at the monomials x to the n. It's a character of irreducible representation. So this is some object that evidently solves a differential equation in set and a difference equation in x. Shift m by 1, just multiply that. I mean, I'm not saying anything for fun. But it is non-symmetric, clearly non-symmetric in set. If instead you upgrade it to an object that will solve a Q difference equation in both variables, which would be something like Q to the power log Z log M over log Q. If I shift Q or M by Q, then I get this. If I multiply Z by Q, this brings out a factor of M. If I multiply M by Q, this brings out a factor of Z. That is symmetric in Z. But there's also, maybe more familiar, there is a level in which you treat both variables additively. So if I take like exponential of x, think like exponential to the n. There's instead of a generalization, there's a limit from this, which is like this. You can go from things which are, you can go down here, and that is symmetric. That's the usual symmetry of Fourier transforms that people sometimes use all the time. And then if you work in the world of usual hypergeometric functions, maybe you see things which are not exactly symmetric. But when you come here, in fact, the symmetry is miraculously restored. That's a very general fact about McDonald polynomials, and a very general fact about the kind of things that we would like to study. And so, where is the say few things about? So there's some subject called three-dimensional symmetry. Is provides an abundance source of special functions we have this property that if I have some variety x and some sort of mirror variety check, there is a way to associate some, maybe call it variety phi of x, have some variables and that function, the terminated cases of that would be exactly equal to if there is a terminating case that would be equal to the exchange of variables. in general there's some kind of t check. So if there were, so McDonald's polynomials are the terminating cases of this function. If they were terminating, they'll be exactly equal. But in general, if they're not even not, they don't have to be terminating, but immediately to a point they solve the same.
Do you get in some limit spherical function on bigger dimensional?
Yeah, of course. Yeah, of course. Solve the same two different equations. And so maybe you should think of this as like that. So you should think of a spherical function. It's not really, you should think of a spherical function. That's not, that's like it's a trace of some interesting operator with some interesting representation space. And in that sense, there's some exact representation associated with the spaces of some algebra. These traces that have the property. But maybe one kind of, this is, I don't know how many of you are more algebraically minded or more analytically minded, but there's kind of key. Well, I don't know if it's analytical. It's analytical in the sense of maybe like if you open the book of Whittaker Watson is called Course in Modern Analysis. If you read the book, it's all algebra, all formula. But there's some analytical point, and namely, what are we supposed to say about functions? So if I tell you this function, the terminating case of this function, actually symmetric. But what does it mean to study? Does it mean that the non-terminating case is also symmetric? In fact, no. It only means that this function solves some q-difference equation in both A and Z, and this q-difference equation, of course, determined by all terminating cases, because all terminating cases they form a dense set of parameters. That's uniquely determined. And so that this means that this function, and if I take in this function, if I exchange this phi, or just write phi, and I write phi. In this case, in general, there's some slightly two functions. In this case, it's just the same function, because so I should say the case we've been discussing all along that had to do with the case. What should be the space X associated to the root system A1? In this case, all of X is the cotangent bundle to just projective line, and that thing is self. That's maybe the simplest possible here. Fair? So this is more generally study McDonald's and then more general than if you study cotangent bundle to some group of Morel. That's what we do. That would be more general. Okay. The first really new example, which is not somehow a classical thing, well, really new. Not fit into this. If I take the Hilbert scheme of n.82, that is also, and it's really kind of interesting special function. Anyhow, going back to the question is that phi and phi check, or phi, all right, maybe I'll write phi check. In this case, it's just phi with A and Z primitive. solve the same equation, but are not the same. And the reason they're not the same, maybe I'll
And they
explain.
just, in this case, the two versions are these special functions related to the things that are used by Diamond or.
No, the Hyman is the constant term in this special function. So this is yeah. So that's just it's like the zero coefficient. So maybe right. I should say that. So there's this function, and there is the two solutions we'll be discussing along that they have to change this function in this and a inverse. Okay? So what did they look like? So if I look at this is my kind of picture. This was z equals 0, and then z equals infinity, and there's a equals 0, a equals infinity. The functions, this function converges for small enough z, and then it hits a singularity around the point. So the singularities of both of these functions no matter. So I write phi for the basis of solution, t and the one with a equals z. So that will have these guys in z. Their poles just start at some point. It converges here and start at some point, and then they start forming some kind of geometric equation. Because once you have a point of pole of your different equation, you get a whole geometric progression. But in A, the poles of these things are, well, here the poles are, the poles, if I look at A inverse, the poles in A, they're all over. They all come here. So the poles really look different. One, in Z, it's holomorphic near the origin. In A, if you take the vector of solutions, the fundamental solution, that it has poles all over. And if you, of course, if you exchange the rho in Z, this will be exchanged. And so this means that there. What does this mean? This means that if I take the vector of functions, phi check, and then phi check. This is with A inverse, kind of that's a vector. I want to express it in terms of phi and phi, the A inverse. This would be some 2 by 2 matrix of elliptic functions. Because they solve the same Q-difference equation. So the fundamental solution to the same Q-difference equation, that means that they transformed one into the transformation between them is a constant with respect to Q-difference equation. It's a matrix of elliptic functions. So for Q-difference equations, you get a funny situation. So there's an analytic point about Q-difference equation is that Q-difference equations are just like ordinary differential equations, except one very fundamental property for Q-difference equation fails. And it fails the famous theorem of Delis that says that the differential equation. What does it say? It says the differential equation, if it's regular in each variable, then it's regular. Something like that. Q-difference equation can be regular in two variables separately, but not jointly regular. So this equation, in each variable they're regular, jointly they're not regular. And what does it mean? That means that if I look at you can see it already here. You can see that if so one feature of a regular equation that the solution has to grow at most polynomial if I go to do single point. And if you see, look here. So if z goes to 0, then I should have written a. Let me undo that. It's expensive. If z goes to 0, but a is not 0, that grows polynomial. If a goes to 0 with z thing, that grows polynomial. But they both z and a go to 0, that grows super polynomial. Right? So even this silliest equation, this solves the equation that if I shift z, I get a. If I shift a, I get z. Even that silliest equation is not regular joint. And the equations satisfied by this function, they're not regular joint. As a result, they have not one fundamental solution, but two kinds of fundamental solutions. One which is holomorphic in the variable z, another which is holomorphic in the variable a. But that if you think that this is a bug, in fact it's a feature, because this is something which is kind of like a Stokes matrix, but it's completely it's completely algorithmic, because you can figure this is instead of well, go to computer Stokes matrix, it requires some actual analysis, but this thing is a question of this matrix of elliptic functions just determined by the need. You look for what is this matrix is supposed to do? This matrix is supposed to take some poles we don't want and produce another poles we allow. So this is about finding elliptic functions with given zeros and poles. And that's this is somehow it's a hard algorithm problem. But okay, maybe this is not in principle algorithmic. But what it tells you, so this tells you something. This tells you this may be what I'm trying to say is this kind of this is an important matrix. And for the reasons because it really determines monodromy and hence the equation itself. Why? Is that because so what's a monodromy for Q difference equation? Monodromy for Q difference equation should be really called a transport. You can write a solution that near say z equals 0, and you can write a very similar solution near z equals infinity, and you can compare them, and that would be your some kind of meromorphic comparison between two solutions. Each solution of Q difference equation is a meromorphic function, and their ratio is then an elliptic function, and that elliptic function is your solution. It's a monodrome. And what is this? Why I'm saying that this matrix determines the monodrome? Because written like this, in A, everything's rational. In A, all the monodrome is gone into the prefactor, which I didn't write. And so if I can the monodromy in Z of this equation, of this solution is trivial. So if I have a way of going by some elliptic matrix from here to here, then I know the monodromy is Z. Okay, now 1 minute left. To summarize, is that this the subject is not only a source of function, pairs of functions like this, it also determines that this has a meaning. This has. And that's the plan for tomorrow. So tomorrow I'll try to explain how you think of expression like this as somehow being something of geometric origin, and how having that information, how you can compute this method.